think my talk is probably slightly different and maybe slightly out of place, but I think you'll probably understand maybe when I finish why we're discussing about this. So it's a lot about security communications, but more looking at new power systems or how power systems are evolving into what's this new technology that we keep hearing about smart grids. So we'll try and see why we think this is getting important. So we know we know electricity is important for us. Any application we think of, when we think of our modern life, it's all run because of electricity. So your lights, your televisions, your cable industry. If you think of it, if we didn't have electricity, we wouldn't be doing any of this. So for us, of course, electricity is key important. And we know more and more people are now constantly being connected. We've got over 5 billion people accessing electricity in a way. So it is an important commodity that's required. And things are changing within the power systems. We've heard of PV cells, we've heard of renewable energies, we know we're running out of fossil fuels and things like that. We want to get more low carbon technologies coming in. So of course there's a drive from the power industry to try and create more renewable, low carbon, green power in a way. But I think there are lots of things that are changing. And that's why I said power systems actually are evolving, right? And evolving to try and bring in new technologies in, which probably didn't exist when you were talking about power systems. Power systems was more to do with power electronics or creating electronic circuits to be able to generate something of that side. But what we now see is things have changed quite dramatically. And there's a lot of communications that's come within the power industry, right? And that's why the grid is evolving. It's evolving because it's bringing in new technology to make sure that the grid can be used more efficiently in a much better way. But now, of course, we need quite a lot of new use cases which needs to be supported. This is quite an interesting diagram which was actually drawn by ABB. It's on their website, which talks about their smart grid work. They're putting in a lot of money into smart grid communications. So if you start looking at, you had traditional generation, where you're generating from either coal or say water, for example, or even nuclear energy. So you're generating electricity. But now you start looking at lots of new things in that whole landscape of power systems. So you've got things like, of course, wind. We all have heard of wind technology coming in, integration of renewables. All of these have a lot of issues in terms of integrating. Some of these don't really integrate it properly. So you need now faster new modern mechanisms to integrate. The concepts of energy storage, to generate something maybe in the day and then use it in the night, right? So you need to maybe store energy. Of course, we need to think of solar energy, PV cells. We know it's really growing, and I'm sure quite a few people here might actually get installed PV cells on their roofs. But you start looking at the comms interface between this. You need very smart communication, very fast communication, some broadband communication to connect all of this together to make the best use of smart grids. We want grid automation, and in general we want smart cities where lots of people are generating, and you're also monitoring things like their usage, but then trying to see how best to match the demand and the response. So here's a diagram which shows where the systems of the smart grids are at the moment, the smart power grids, how they're actually generating and where the issues are and what's changing. So if you look at the bottom, this is what traditional grid was. You were generating on one side, bulk generation on one side, from a thermal power plant to a water power plant or whatever power plant generating power. Send over high voltage transmission lines, which you can see those big pylons going through the country, to small distribution cells where you step it down to slightly low voltage, and then you bring it to your customer. So this is the electrical system, has been there for quite some time. The problem was, or I wouldn't say a problem, one of the issues is, it's all unidirectional. You generate on one side and you push power on the other side, and the other side is where the load is, which wants that power. Right? Things are changing quite a lot. You're now generating on the other end as well. You've got homes generating from the PV panels, right? But how does the grid know, or the actual generator know what you are generating on the far end on that side? So again, you need to start thinking about some form of communications. And what smart grids allows you to do is it combines things like new opportunities from energy markets, right? So anyone who's got PV cells will know you've got a feed-in tariff. It's very much fixed at the moment, maybe not very lucrative also. But the way industry is moving in forward is going into what's called real-time pricing. So you'll get not price for day price and night price, like probably what you get now, but electricity prices will change every hour, right? Which of course means now your smart applications, your smart appliances within your home. One of the previous speakers was talking about Internet of Things, where you have lots of things connected. Now all of these who want energy will now need to start talking about how much energy do they want and where should they get that energy from? Should they buy it from the grid, or should they actually generate it themselves at that particular time? What would be very profitable? And of course, you've got to be able to manage operations and then be able to provide that service across all these different places. And when we talk about getting the grid, we're not talking about small grids, we're talking about national-wide, international-wide grids. You've got a lot of assets. So what the smart grid actually talks about is you now have all of these will have intelligent electronic devices which are constantly measuring all kinds of parameters, making sure they know exactly what's happening. So whether they're monitoring what's generated at the bulk side or as well as what's being generated at the consumer side. And these consumers are no longer just consumers, they become prosumers because they're producing as well as consuming. Right? So you have this new concept on that side. But all of these now, every pylon is connected, every substation is connected, every DNO, everybody's connected now to the internet. Right? So this is a new form of Internet of Things, but more to do with the power systems. And that's what comes with, or creates this new technology, some of you might have heard, the Internet of Energy. Right? So you now have all energy assets also connected to the internet. And of course, they need quite a lot of fast broadband communication between them because they've got to make a lot of real-time control decisions. Of course, what you now have, earlier everything was connected only that way. Now you've got all these new technologies, which means you now, if you can support that, with these new energy markets, the new operations and service providers, you now get lots of different, extremely interesting use cases, right? So you're looking at things like dynamic pricing on one side, to how you get renewables added to your systems, smart metering. I'm sure you heard of smart meters at the moment, but they're not really smart. All they're doing is measuring and just wirelessly transmitting some information. So what's going to happen in the future is you'll be able to even control your appliances. We've got PhD students who are looking at how do you smartly control appliances based on when they should buy energy and your future predictive requirements, right? So maybe automatically you could schedule when your washing machine should run to make sure it's cost effective. Right? And of course, things like even electric vehicles, it's going to become very big, right? We've seen the government push quite a lot on electric vehicles, and that becomes quite an interesting perspective. You know, how does it all come in together? Electric vehicles are in a way tricky because they're actually a prosumer in a way. So they will store energy for you, right? But they'll also consume energy. You might be able to use it for some time, but then be able to give it back and sell it back to the grid when you can make money out of it. So you've got all these fancy ways of using market analysis to look at how consumers get involved. And of course, we're talking about ubiquitous network sensors which are connected everywhere and communicating with each other. And there's a lot of work that's being actually done, not just within the grid system. Now the grid system's already people have specifications. The IEC actually has already defined quite a lot of specifications on how some of this communication can actually work. And they've defined, you see, if you've got your generation customers, all of these, you need this very strong communication backbone in order to really realize this vision of smart grids, where everybody can actually talk to each other, all the sensors can talk to each other, and you know what is happening at every asset. So of course, what we need is a strong broadband backbone network, which can maybe wired in parts, wireless in parts, which can actually share this information in real time. That of course gives you all these different nice functionalities which the smart grid wants. Now, the issue of course comes, traditional electrical systems is not a comms system, it's got nothing to do with us. I'm also from I'm a comms person, my background is communications, not really power. But what's important is we're now trying to look at how these two overlap with each other to make sure we can get these things working in the way we want. So you have a power system layer overlap with a communication system layer. So your power system layer, like I mentioned, you've got generation on one side, transmission, distribution, and finally consumption at the user end. And similarly, if you start looking at, if you wanted to connect all the comms or all the assets together, you have a comms layer, a communications layer. You've got a home area network, which are all your smart appliances, your fridge, your television, your washing machines, your dishwashers, everything connected together, right? Connected to the internet. Every home will have a smart meter, which is constantly monitoring the user's patterns, the profiles, also maybe able to control some of these appliances in the future based on what way we go. a lot of these smart meters or smart homes then start connecting together to create a smart network or a smart city, right? Which is now basically your area network or neighborhood area network. So you've got a home network or a home area network going to your neighborhood area network. And then, of course, you can pass that data back through wide area networks, high-speed broadband, going back to your control centers, right? And again, you could do quite a lot of things like aggregating a lot of data. So you might not want to send individual information from users, but maybe collectively as neighborhoods, so you can know exactly how much a particular estate might require in terms of energy requirements, energy loads. So you're generating, you know exactly what you need to generate. So you probably don't need to go at individual basis, but you might want aggregated information. So you can have things like aggregators and concentrators. And some of this could be more wireless when you start transmitting over large distances to your operators. So you then get this double layered technology system where you've got a power layer and a comms layer which needs to work together. And what's important is everything needs to be combined together. So in power systems, power electronics has very strong mechanisms to make sure they can actually monitor, for example, power transients, loads, etc. So in case you have fluctuations, it will automatically, using smart control algorithms, try and monitor and manage what it can. But that means it needs some really very fast real-time control algorithms running behind. And of course, when you start getting information from many people, you can make much better decisions, because you're not making decisions on just what you measure, but you're actually making decisions on many people are measuring, so you can control many things in the right way. But that creates more problems later. So we need to make sure that the communication infrastructure is reliable and is pretty fast, so that you can make these real-time decisions. This is not new. I mean, there's a lot of standards that have been specified within this area in terms of communications. So when you start looking at what, for example, IEC or the IEEE specify, they talk about things like, let's go from bottom, home area network, have their own technologies. You can use things like Zigbees, Wi-Fi's, etc. to connect all your appliances together. When you start looking at neighbor area networks, you start looking at technologies that are like WiMAX, other cellulars, maybe even broadband cable connection, connecting all your estates together. And then you can start going to wide area networks, streaming and sending data back to your control center. And there's a lot of these technologies now that fit into this area of communication for the grid. So it's not one technology or one comms technology. We need to think about what's the role of all the different comms technologies. And let's now start talking about what are the issues and problems, so we know exactly where we're heading. This is a table which is taken from the IEC 61850 standard, which talks about requirements in terms of delays and throughputs for some of the messages that flow within power systems. So if you look at, for example, substation information. So when substations have to talk to each other, they will be talking very real-time, very fast information, so that they can make decisions on what they need to do, how their control algorithms are running, so that you don't have a blackout. So in case you suddenly have a huge load, you don't want a blackout to take place, so you want to make sure your algorithms will manage it. But you're looking at things like a few milliseconds, 12 milliseconds to 20 milliseconds for some of these. This is only on average, but there are messages like loose messages where there are very strict deadlines of 4 milliseconds. You can't delay the message more than 4 milliseconds. So you're looking at very high-speed communication that's required, and high-speed reliable communication that's required. And no matter what you look at in terms of any of these applications, apart from standard smart metering, which can be done relatively easily without very real-time requirements, most of the other requirements of the power industry is very high-speed, high data requirements. So these are the two most commonly used comms protocols which are used by the power industry at the moment. So DNP is used more in the US. It's a US standard used for their systems. It was done quite some time back by GE. But of course, we have the IEC 61850, which is now trying to unify everything across the globe, trying to make sure all the grids are compatible in a way. So they came up with the 61850, which talks about how they can use Ethernet communications between, say, for example, substations and other assets together to share information. This, of course, information is then used for all their real-time control algorithms to make decisions in a better way. And here are some of the examples. Again, you're looking at you're looking at orders of what are the delay constraints, the maximum delay constraints that are acceptable. Things like 3 milliseconds. So you talk about really very fast communication requirements. And then you have a lot of these other technologies which probably can't provide you. So you then start getting limited to what you need. When you start looking at the number of assets, you're talking millions of assets all around the country, which are all sending data at these speeds, or sending a lot of data with such requirements. You start looking at, well, maybe some of the standard wire systems may not be useful. What do we do? Now, my talk is on security, not really on comms as such. So I'm looking at the security angle of some of these problems, and why security probably on the grid is important. But I have this slide just to also show the security performance trade-off. We all know every time you add security, things get a bit more difficult because you may be encrypting, you're decrypting, you're going to add some delay onto your network. If you're going to do that, basically what you're saying, your performance is going to degrade, right? So you need some time in order to do your security manipulations. So here's a diagram. The table on the left talks about different encryption algorithms, your standard AES, triple DES, DES. These are standard encryption algorithms, and how much time they take if your input size of what you're actually trying to encrypt increases. And you can see these are again in milliseconds. So yes, 56 milliseconds going up to 1300 milliseconds. And again, the bigger your size of your data that you want to encrypt, the more time it takes. So it's very similar to if you want to compress a file. If you've got a small file, you run a zip, it takes less time. If you have a very big file, you try to zip it up, it takes more time. So of course, the higher the size of the data, more time. This shows that if you were doing it with a fast computer, well, fast at that time, but not really fast, but even if you're looking at faster computers compared to standard ARM processors, small embedded systems, right, there's a stark difference in terms of the speed requirements, or speed that it is. So a computer might take 8 milliseconds to run a DES algorithm, but an ARM system might take 192 milliseconds to run the same. Right? Now a lot of these smart systems that are going to be put across the country to connect all the pylons together, connect all the substations together, they don't have fast dual core or quad core systems running on that. They've got small embedded systems running there, right? Which of course means they're somewhere in that between 8 and maybe 192, right? Or maybe still they're not really at 3 milliseconds or 4 millisecond requirements. So every time you now start thinking about adding security to any of the power mechanisms or power messages, you start thinking, well, will I meet my delay constraints? The real-time constraint requirements are really high. So what do we need to do, and why I think security is very important? We know the industry is moving towards that, or the power industry is moving into that, and I'm sure there's going to be a lot of communications or talk between power industries and the comms industries and the cabling industry to try and see how these different industries can support the power industry to connect all these different millions of assets together, right? And we know there's these kind of talks already taking place. But the problem is, from my point of view, is a lot of people are not really looking at the security aspect, and we might have a lot of problems. So we know we need a lot of security, we need different types of security, you need multiple layers of security, right? You can't just have one security and say this is it, it's all done. You need different types. Every time you talk about security, people say, oh, we'll encrypt the data. But encryption is not the answer for all security. And we'll see that. So, you need to authenticate people. You need to make sure data is, there's data integrity, data hasn't changed. Encryption doesn't mean to solve all the problems. We've got to also balance the cost. Right? So more cost, more security, keep adding, this cost will keep increasing, which means you now need to then try and find the right trade-off. And there's a slight change in the paradigm in a way. So if you look at normal communication systems, for you, when you say doing internet banking or etc., any application online, you want high confidentiality. You don't want people to know exactly what your transactions are. So confidentiality becomes very important. You then need integrity, right? And things like availability and all is okay. So if you type HSBC or whatever website, and if there was a slight delay, you probably didn't care, even if you could probably try after some time. But what's important for you as users is once you're connected, you want that link to be very secure. With the power industry, it's very different. Power industry doesn't care about confidentiality. The only thing that power industry cares about is business continuity. Your power cannot go down. No matter whether you're attacked, no matter whether your fluctuations, no matter what happens, you continue providing power. You cannot stop that, right? If you stop power to a country, that has a lot of knock-on effects. If you're talking about no power to hospitals, no power to schools, no power to airports, that has a really big knock-on effect. So the power of the business continuity for the power industry is extremely high. So the availability is more important than anything else in terms of security. Of course, you can have deliberate attacks, you can have accidental attacks. You've got lots of different types of attacks, which we know that happens on the internet. And of course, now when you start connecting your power industry to the cyber world, you have a lot of cyber attacks taking place on the power industry. What we need not is to make sure we have very strong end-to-end communication or end-to-end security to also provide or protect from any man-in-the-middle attacks or any attacks that are taking place which are not properly secured. So what's important in terms of goals is you've got to be able to prevent any attack. You've got to make sure you've got a strong system there to be able to prevent any attack. But having said that, you can never prevent everything. You will always get attacked. So you then need to be able to detect any attacks that are taking place. And then you need to recover those attacks in such a way so that you don't lose your business continuity. That continues. So why is it a problem for the grid? Or why is it specifically a problem for the grid? Security is not a new topic, and people have been doing that for lots of years. There are quite a lot of issues which create problems. First, the scale of the problem. If you look at all the assets, the substations, the DNOs, the homes, everybody connected together, that's a different scale. Right? When you want to start connecting all of these different types of devices together, what do you do and how do you do? Creates more problems because you now have a lot of places of attack, not just one place of attack. Physical security, yes, that you have npower or wherever, but they don't, your whole network is not with you, which is very similar to your cable industry. When you lay down all the cables, you may be sitting in your office, but all the cables, all the assets are not under your vision. Right? You're talking about infrastructure across the country. In power systems, there's an implicit trust between devices. So when a substation sends you a message, you trust that substation because at the moment, this is a secluded network. It's not the same network as your public network. It's a SCADA network, which is completely different. But when you start removing that and connecting it to the public network, now you need to start thinking about, is this message that I'm actually getting, is it really from a substation, or is it from a hacker who's pretending to be a substation? Right? So that implicit trust disappears. The lifetime of the power system is very important and a big problem. When power systems or power grids or power plants are set up, they expect they're going to run there with the comms infrastructure, with everything for 40 years, at least, maybe more. Right? Do you remember what was the computer you were using 40 years back? I'm sure you know. Right? So if we put some security mechanism now, how do you know that will still work 40 years afterwards? Because you'll have to keep changing. But that's very expensive for the power industry to keep changing, keep upgrading. They don't like doing that. So they like there's a lot of money required to set up everything, and they don't really like systems that need to be constantly updated because of the expense. So that's an issue. Business continuity I've already talked about. Customer privacy. I'll come back to that later also. We want to monitor, of course, what we're doing, but that creates privacy issues. You've got this big problem about you want to start using IP systems, standard common off-the-shelf systems. We know these are already prone to attacks. Right? So is it really a good idea to start using some of these technologies which may not be very good? But we know it is. We've been using this everywhere, so we want to use that. But we want to make sure it's done secure. More stakeholders, because you have a lot of people. So in terms of security, what do we want to do? We want quite a lot of things. We want confidentiality. We want to make sure that nobody knows what your data is, what the informations are. We want integrity, because we want to make sure nothing gets changed. So when a message is sent from a substation, it is exactly as what you receive. Nobody can change it. Availability, that the network is always available, even if it's attacked, even if it's under attack, it's still available. So if you've got a DOS attack on a substation, your substation can't be shut down. You can't do a reboot. It has to keep running. Right? So how do you have mechanisms for that? How do you authenticate, authorize people? And how do you do things like non-repudiation? How do you make sure your parties cannot deny sending or receiving the data? So types of attacks, you've got passive attacks and active attacks. So we have quite a lot of attacks that we know the cyber world is prone to. And if we, of course, connect the power industry to the cyber world, they'll be prone to similar attacks. So when you start talking passive attacks, these are more general attacks. You don't really get bothered about it because people are not trying to actively damage your system, but they just want to listen, eavesdropping, traffic analysis, see who's communicating with who. So those are the kind of attacks that they will do. But usually passive attacks will lead to active attacks, when then once they know what's happening, then they will try to actively damage the network. Right? So there could be different attacks like masquerading, somebody pretending to be somebody else. So once a hacker starts pretending to be a substation and sends a message to all other substations to shut down, kind of maybe issues. Replay attacks. right? So you might save a message, the message is correct, but then you keep replaying that again and again every few minutes. Now, the message is absolutely correct, it's come from the right person, it's just an old message. So looking at replay attacks. Message modification, of course, very common one. The substation sends a message saying everything is okay, and you remove that saying everything is not okay, right? So then, of course, there's a problem, so then you need to start controlling it accordingly. And of course, DOS attacks, we've heard about this quite a lot of times. You send a lot of millions and millions of messages to a computer. What that computer has to do is keep checking every message, reads the message, and says, oh, this is a bogus message, throws it. Then reads the next one, bogus message, throws it. But it's got a big, it's filled its whole buffer, it's filled its RAM with all this garbage, which means anybody who actually had to send a message can't send a message because the memory is full. So the same thing could happen now here. So if the substations have to communicate, and you start bombarding it with bogus information or rubbish information, then it would not get the real messages from other substations to actually start communicating. So you can have things like device attacks, you can have data attacks, you can have privacy attacks, or network availability attacks. So quite a lot of different types of attacks that are possible within the smart grid system. How are we doing with time?
You find another 10 minutes.
Okay, perfect. So let's look at some examples, right? If you look at this example, this is quite a nice photograph which is actually on the website from Gridstream Collectors. This is a very big power system DNO in the US, right? And they were boasting about how good the system is because they're one of the first ones who've got smart grid technology where they've got pylons connected now to the internet, right? So they've got these boxes which have connected using Ethernet comms, then wirelessly they can collect all that information and send it. So they know exactly what is happening on all their assets. Very good. But really, can anyone see a problem with that? Anybody can just stand there, take that Ethernet cable out, connect their laptop in, and do whatever they wanted to do. Right? So, of course, the power people, I hope there isn't one here, but they don't really understand the comms problems or the security problems. They're excellent in the power side. Right? But when you start doing these kind of things, you not have to worry. Really, there is a problem. So you have an easy way of doing a device attack. You just remove that device and plug your laptop in. And that's a device attack. Now you can pretend to be that device and you can send whatever you want to send. Right? So looking at, you could replace a legitimate device, you could reprogram that device, you could just go pick that up, reprogram and put it back in. Right? You can do anything like that. So of course you can now have device attacks. In order to prevent any of this, you need strong authentication mechanisms. You need to be able to authenticate which device it is. No matter which device is connected, it could have been reprogrammed. You always have to assume that this could be a malicious device. So even every time you start communication, you need to first check what that device is or who that device belongs to and do some kind of an authentication before you accept messages from it. Data attacks, which is the more common attacks. Most of the time you might not have access to physical substations. You probably wouldn't want to go into a substation to try and damage it. But yes, you might be able to intercept data when you're on the internet because now all this data is going to go through the internet. So things like false data injection. Somebody pretends to be you and starts sending wrong data to the substation saying, we have a fault in that particular estate, increase power generation or something like that, and you start generating a lot more power. So you can easily start doing those kind of things. Message modification, modify your message. Man-in-the-middle attack, where of course now you've got somebody in between two substations and can keep changing messages that are being shared between the substations. So again here, you talk about data authentication and running algorithms on data integrity, making sure that can be easily proved. So you've got to make sure that everything that anybody receives is what was sent by a sender, and nobody in the middle has actually modified that message. So you want some data integrity mechanisms there. Data delay or replay attacks, again, very, very crucial for the grid. Not so crucial for general comms or for internet communications, but very strong, very important for smart grid systems. Because smart grid systems are real-time control systems, they're industrial control systems, they have some very strong control algorithms which their turnarounds are a few milliseconds. So they want messages coming in very quickly, they're making some decisions on what needs to happen with the power electronics, what needs to happen with the generation. And all of this is done in a few milliseconds. Even if you delay a few milliseconds, that's a big problem. So you've got PMU systems which usually will measure something like, I remember, a million cycles a second, something like that. So if you delay these million messages that are coming in by a few seconds, or even 1 second, the whole cycle is gone. So you don't know what decision to make because you've only got maybe information for some of the assets, the other asset information hasn't come. So you really can't make a decision. So your algorithms now need to change in a way to be able to compensate for attacks. And of course, these people are not prone to attacks, so these algorithms don't exist anymore. So we need to make sure there are mechanisms there to make sure that data is timely. It is current data, it's not old replayed data. This is quite an interesting work, and probably we will know, and I didn't know about this till I started working very closely with a power specialist, that a huge amount of work is being done in the power industry to look at load profiles. When do people want energy, right? And this is where the problem really comes. So this is actually for UK, any typical household, you'll have something like a refrigerator running, keeps coming on and off, the compressor keeps coming on and off. You wake up in the morning, you take a shower, etc. You have a washing machine run. For UK, one of the biggest problems is this 4 o'clock to 6 o'clock kind of peak when everybody finishes, goes home, switches on the kettle, switches on the TV and stuff like that, and you get this real big peak. And that's where the problem is, because if every house is doing that, during those 2 hours you need a lot of power, right? And most of the power industry is just trying to deal with these peaks. So if you think about several million people trying to do that at the same time, you now have a lot of power demand. And that's what I think they want to curb by bringing in renewables, saying at that time, if you just started using your PV cells, your solar cells and all, energy that you generated from that, then the grid doesn't have to support that really high demand during that time, right? So there's a huge amount of work that has been done. Lots of research organizations, industry, everyone trying to model that in a very nice way, right? But unfortunately, as a security person, I always look at the negative side of this. What's the negative side of this? Customer privacy, right? Do we really want all that information at that every detail of what's happening to you in your house to be known by anybody, right? So you'll have hackers, attackers, theft, everybody getting access to their data or could get access to their data. So they will now know when do you actually wake up, when do you go to sleep, when do you go to work, when do you come back, how many children you've got at home, when did you go to school. So effectively they'll exactly know what you do in your daily life, right? Very easy for them to now, come in and burgle you because they know nobody's at home. Because they're in real time monitoring that, and when they suddenly see, oh, nobody's woken up, nobody was there last night, so which means you've probably gone on holiday, right? Let's go in. There's nobody at home, right? So you start looking at privacy stuff. You can, of course, then go and start getting more intimate information which you probably don't want anybody else to know, right? So you need to be able to, you need that kind of privacy as well as you need this information to be able to better manage. So how does security work in that case? Right. So we need quite a lot of different things. We need data confidentiality. We need to be able to encrypt this data so that nobody sees this data in the middle, right? You, of course, have this load profiles. Your smart meters are generating it or recording this and sending it to the operators, and the operators probably want it, but nobody in the middle should be able to see it. Maybe, do I really want the operators also to see it? I don't know. So there's a lot to look at. Who should have access to this data? Who controls this data? Who controls the users of it? Who keeps this data? Right? All of these questions need to be thought of carefully when you look at customer privacy. One key problem is the way you would provide privacy is you will encrypt all the data and send it. Now, when you encrypt data, you're encrypting one person's home's data. But we talked about aggregators in one of the slides where you can have a lot of data coming from different homes. These are, you may not be big data or small data, out of data. You combine all of that, aggregate it, and then send it. But when you start doing aggregation of data, which is important because you don't want to waste bandwidth upstream, but then you can't aggregate data, probably, or one problem is aggregate data if you want to encrypt. So if you encrypt all the data that's coming in, then you can't really perform any aggregation on it, or at least easily. You need some novel mechanisms to be able to do that. Availability attack, we've heard about these DOS attacks, where you can attack different substations, different assets, by sending a lot of different types of flooding data. You could even do things like jamming. If you're using wireless technology, you can use jamming signals to jam it, and of course it's not going to listen anymore, it's not going to receive any of these messages. Then we need mechanisms to provide some kind of security for that. So we've talked about the problems. Maybe I'll just talk a little bit about also some security solutions. It's not that that nothing's been done. There's a lot of work being done. This presentation is actually part of the SITARA project where we're also looking at different novel security solutions for the grid, for some of these issues and some of these problems, how you can solve some of these things. So things like confidentiality and privacy, of course we need to encrypt data, but it's trying to look at what encryption algorithms will work, and there might be different encryption algorithms running for different links, depending whether they are fast computers or small assets, depending on the kind of information and the importance of the information, and of course leading to the impact. So, you know, if you did get access to that, what was the impact? So you will use encryption algorithms accordingly. NIST has also suggested a couple of algorithms in terms of what can be used. But there are things like anonymization, techniques of anonymization to provide privacy. So instead of saying, here's reading for this house, you don't really need to know it's this house. You just need, the operator just needs to know, here's the reading for somebody in that in that estate or in that city, right? Effectively, the operator only needs to know what's the total load and what needs to be generated. Doesn't need to know individual person, right, or individual household. So you can have lots of anonymization techniques where you collect the data, aggregate the data, and send aggregated data, collect the data together, saying this whole estate will need this much energy now, and this is the predicted energy. Right? Of course, what you need is then trusted aggregators in the middle who you trust. So once you have these kind of aggregators, you can provide that service. You can do things like homomorphic encryption, which we've also looked at previously with a couple of other PhD students, where you can encrypt data, but then run some homomorphic encryption on the encrypted data, so you can still aggregate data even after they've been encrypted, right? So you've got a lot of encrypted data coming in from different sensors. You can combine it, you can aggregate it, and then send the aggregated value. So even though it's encrypted data, you can do what's called aggregation on top of that. You can do perturbation models, which are basically adding random noise. So you know what the noise has been added, and the operator knows what the noise has been added, and nobody else in between knows. So they don't really know what is the real readings and what are the noise readings. You can do data obfuscation, which is where your batteries might, or your smart meters might have some techniques to conceal how much energy is actually used, and actually maybe exchanging information in a different way. There's a lot of work which has been done on physically unclonable functions. So you've got some new electronics which can't be cloned, so you know exactly who it is. So this is more used for authentication. You can use your standard HMAC systems, your hash-mapped message authentication code systems, which are used in your standard communications, which can of course be used for authentication and integrity. Availability is always tricky. It's always hard to manage. We need strong intrusion detection systems, strong systems to be able to detect any DOS attacks. You'll have to have a combination of different ones, whether it's signature-based, protocol-based, or specification-based, or even anomaly-based. So you might have to monitor patterns of data and see if there's anomalies in the patterns of data, which might mean there's probably an attack taking place. So you'll have to look at all of that. So just to show, I've only got 2 slides left, I think, so I should be in time. This is just to show the scale of the problem. So NIST has actually come up with this security, I wouldn't call it a security, I think it's a smart grid architecture in a way, but defines the security interfaces, says where all security is required in just a single interface architecture, and it's got about, I think, 36, last time I counted, 36 interfaces which require high security. So in order for the smart grid vision to work, in order for all the parties to work together, all the stakeholders to work together, we've got 36 interfaces which require different levels of security, different types of security, and a lot of these are very high security. But again, on the same side, they have very strict comms requirements in terms of their delays, their throughputs, and their quality of service. So it's how does one manage that together? How do you make sure you keep providing the security, making sure you don't lose the packets, you're still reliable, but you still meet the QoS requirements. So I've got just one last slide. This is a general slide just to show that it's not one size or one shoe that'll fit all, in terms of you can't just run one algorithm and say we've sorted the problem. Everybody will have to look at all kinds of things. We're looking at device tampering on one side to authentication confidentiality. You'll have to look at filters, firewalls on one side, authentication systems. All of that needs to be looked at when you start looking at security for the grid. But what's important is first is to look at the underlying communication architecture properly, because then that will also give them the kind of security that is possible with that architecture. So that brings me to the conclusion. So like I said in the beginning, smart grids are evolving. Right? Smart grids is the future. The power systems are not where it was traditionally. There's a lot of communications taking place now in these smart grids. We've been talking to a lot of DNOs, power grid and all, and they're looking at a lot of ways to communicate this data. And again, when you start collecting data from every household, you are looking at broadband kind of data. Of course, we need reliability and security. We need to make sure this communication information is reliable, because there'll be power decisions on the power layer being made by the comms interface, the information coming in from the comms side. And so, of course, the security for the power grids adds or is quite important, but provides quite a complex challenge. Still in infancy in a way, because of course the current power systems, power grids have not become smart, right? But they're transitioning into that. That's where they know in the next 5 to 10 years that's where it will go. So all this information will have to be, or all these things will have to be sorted in that quick time. We know there are large possible attacks that are possible, whether it's data attacks, device attacks, privacy attacks, or even attack on the availability. So we, of course, need to look at all the security mechanisms that will be required for the whole grid, because any one spot that is weak, any one spot that is not properly secured, will mean that the whole grid is vulnerable to an attack. And you can attack the whole grid from any one point. So a lot more work still needs to be done for that security for this future grid. Okay, so thank you very much for that.